Hello everyone, my name is Bob Schleicher. I'm responsible for product development with Kessil Lighting as well as our sister company Dicon LED. And I'm very happy to be here at the Grow 2010 show here in sunny Los Angeles to talk about the underlying technology behind Kessil Lighting's LED grow lights and how we're intending to lead a spectral revolution in grow lights using that technology. There's been tremendous progress over the last 30 years in particular in developing a broad variety of nutrients, special recipes, special formulations that have really optimized the various parameters associated with plant growth. But in contrast, we don't think there's been nearly as much progress in the developing of custom light spectrums, that other critical element of plant growth, light. Most of the available lighting for indoor plant growing is based on broadband light sources, whether it's fluorescent bulbs or metal halide bulbs or high pressure sodium bulbs, which in general provide broad spectrum lighting that more or less attempts to imitate the light quality of natural sunlight with varying degrees of success. But with LED lighting, there's the possibility of truly tailoring the spectrum for specific applications and also for developing very good recipes for indoor plant growth. Why LEDs for this spectrum revolution? LEDs provide a specific wavelength. A given LED chip only provides light over a fairly narrow portion of the spectrum. You can find LED chips that range anywhere from ultraviolet to deep blue and indigo, to blue, to green, to various shades of yellow, amber, and red, and even LEDs that emit no visible light and only emit infrared wavelengths or heat. This might sound like a disadvantage for LEDs because they are narrow spectrum, but by using multiple types and wavelengths of LED chips, you can actually create a custom spectrum that's tailored to the application that you're seeking to achieve with plant growth. It's also true that photosynthesis only uses some wavelengths efficiently. The plot that's kind of hard to read on the upper right shows the sensitivity of chlorophyll A and chlorophyll B to different wavelengths of light, ranging from visible blue at the left to green, then yellow, then red. And you can see that it's most sensitive to blue light at the lower end of the spectrum and red light at the upper end of the spectrum, and is relatively insensitive to and unaffected by the green and yellow wavelengths in between. Unfortunately, most incandescent and fluorescent bulbs put out a lot of their energy in that green and yellow portion of the spectrum. Most of that energy is essentially wasted on plant growth, and that has very minimal effect on plant growth. So our basic principle at Kessil Lighting is provide the wavelengths that are needed for plant growth and are very efficiently used for plant growth, and none of the extra wavelengths that are just wasted essentially. It's also true that various aspects of plant growth, whether it's vegetation, flowering, blooming, fruit production, etc., are influenced in different ways by different portions of the spectrum. And I'll talk about it a little bit as we go along. A little LED 101. What are LEDs? LEDs are light-emitting diodes. They're fabricated by combining P and N type of semiconductor material. There's such a thing as a regular LED that doesn't emit light. Those are used in electronic circuits, various applications, and they conduct electricity in one direction but not in another. In the case of a light-emitting diode, however, when it's conducting electricity in one direction, it's also emitting light. The wavelength of the light that's emitted by any particular LED is a function of the materials with which it's made. So by varying the specific mix of materials used to fabricate the active light-emitting area of an LED, we can produce specific wavelengths. As I mentioned before, they're very narrow-band light sources. They produce specific wavelengths. The other thing that's key about LEDs over the years is that over time they become much more efficient at converting electrical energy to light energy. LEDs have been around for 50 years or more. Early LEDs were basically used only for like little indicator glowing dots on a screen or something. But over time, high brightness LEDs have been developed that have tremendously higher light output and do a much better job of converting electrical power into optical power. The other thing that's true is that with advances in LED processing and packaging, it's also possible to put more current, more electric current through an LED chip than ever before. So even with a given efficiency at converting electricity to light, we've also made advances in putting more electricity through the LED chip so that more light output comes out. And in fact, the light output of an LED scales essentially proportionally with the amount of current that's driven through it. So over time, the currents that are used in high brightness LEDs have gone up. It's now fairly typical to put a third of an amp through any individual LED chip. And in fact, we're driving ours at about half an amp. And over time, that may go higher to as high as 1 amp through each LED chip. And the light scales up more or less proportionally. The pictures at the bottom are showing bare LED chips of a variety of colors. This is maybe more than most people want to know, but there's basically two families of LEDs. Red and orange LEDs made with one set of processes, and those chips tend to look yellowish or red even when not illuminated. Blue and green LEDs are made out of other materials, and they tend to look actually more whitish when not powered, but when they're powered, of course, they emit blue or green light. Not all LED chips are the same. We make our own LED chips at the Dicon LED, sister company of Kessil Lighting. And there's a couple of tricks involved in making a good, efficient, high brightness LED. The two challenges are to get as much light out of the surface of the chip as is possible. That's light extraction efficiency. And one of the tricks that we play to do that is we actually do some nanoscale surface texturing of the LED chip, which not everyone does, to create multiple paths and more surface area at the very fine nanoscale level, such that light is emitted in all directions and you get more total light output. Although it is worth pointing out that the light is only going up out of the chip. There's no light going down out of the chip. The flip side of the problem, though, is that with putting more power into LED chips, the electrical power dissipation is increased, and you can generate a lot of heat out of each of these tiny little chips. So the other key area of LED technology expertise is getting the heat out of the base of the chip where it can be dissipated in some form of heat sinking mechanism underneath the chip. And we also have some proprietary technology in that area. This is, the pictures on the right, by the way, are showing our clean room facility, which is up in Richmond, California, which is in the San Francisco Bay Area, more or less next to Berkeley. And we do all of our own LED chip fabrication in that clean room facility, as well as packaging of the LEDs into matrix arrays. Traditional LED vendors package LED chips one chip at a time. Most commonly, the chip is bonded onto a carrier, which might be plastic or ceramic. And then a simple, cheap little lens is put on top, which is often made out of plastic. And it's a fairly cost-effective process, but the performance and efficiency of this packaging method is not that good. It's especially not very good at extracting heat from the LED once it's illuminated. To get that heat out, the chip bonding process is very critical. The chip bonding process refers to the mounting or attaching of the LED chip to some electrical circuit that it needs to be connected to. So it needs to make electrical contact where appropriate, but it also needs a carrier to sit on, and also to dissipate heat out of the bottom side of the LED chip. A typical method for packaging LEDs is to just use epoxy, essentially glue, to attach the chip to the underlying carrier or substrate, which might be made out of a plastic-like material or a fiberglass-like circuit board material. And this is not very good at getting that heat out of the bottom of the chip. So the chip, as a result, runs fairly hot and heats the mortal enemy of LED chips. For every 10 degrees that an LED chip runs hotter, you're going to drastically reduce its lifetime, as well as reduce the light output that you can achieve for a given amount of current. It is a low-cost process, however, so what we find is a lot of the LEDs that are out there in the open market tend to use this lower cost method that just doesn't perform very well. Our approach instead is to use a metal carrier, and we've developed a patented process for implanting electrical patterning or electrical traces to carry current to the LED chips on a metal carrier that conducts heat out the bottom very efficiently. It's a little more costly process, but it also results in higher performance for the LEDs, higher reliability, and longer light time. We also have developed a process for mounting multiple LED chips in a small, confined, dense matrix array. Here's that typical approach again, with LED chips mounted one chip at a time in a fairly simple holder or package with an inexpensive plastic lens on top, and typically a small metal reflecting cup to try to get some of the light pointed upward. But our approach involves putting large numbers of LED chips on a single substrate, packed very closely together. This photo here is looking through the lens that's mounted on our substrate. There's actually 21 LED chips separated into multiple channels, so we can use different colors, any mix of colors that we want. In fact, there's also the potential to control the brightness of portions of the LEDs separately if we want to do that. A single high-quality glass lens is then bonded on top, which gives very good optical performance, very uniform spreading of the light. And then underneath that is that metal carrier board, which extracts heat at the bottom of those 21 chips and lets them run very cool for long lifetime and high reliability. And then we couple that with a very effective thermal management system consisting of a heat spreader that the metal carrier board is bonded to, and then a finned heat sink, and we use a small fan just to blow at relatively low velocity, a little bit of air over the heat sink, so we can get the heat dissipation associated with 21 high brightness LED chips very effectively out the back of the light source. The total electrical dissipation of this 21 chip array is, including the driver circuit that is converting electrical power input into the current that the LED wants to see, is about 36 watts. And then we're typically getting 400 or so optical milliwatts out of a blue LED chip, and on the order of 300 optical milliwatts out of a red LED chip in terms of optical power output.